Hi all, this is Mrs. Sumati Kutin from the Department of Mathematics, KC College, Churchgate. Today I'll be presenting a lecture on the topic Binomial Distribution, which is chapter number 8 for SYGC Science students of Maharashtra Board. Hope you guys will sit back and enjoy this lecture. Now, to understand this topic, let us just take a peek into the concept of probability which you have studied in your earlier classes. For example, if a coin is tossed once, then the tree structure is as follows. Throwing the coin will be called as a trial, and the outcomes which you get, that is head or tail, they are called as events. The sample space is denoted as capital S, equal to collection of your sample points, which is H and T. So probability of an event A is denoted as P of A equal to N of A upon N of S, where N of A stands for number of cases favorable for the happening of the event A, and N of S is your total number of sample points in the sample space. Here the event A can denote either the happening of the event head or the tail. So in this particular example, P of H is equal to P of T, that is probability of head is equal to probability of T, which is equal to half, or the total number of sample points in the sample space is 2, so N of S is equal to 2 power 1 when a coin is tossed once. Now we go for the next example, when a coin is tossed twice. Then the tree structure is as follows. For the first toss of the coin, you may get a head or a tail. If you get a head in the first toss, then the second toss can be either a head or a tail. But if you get a tail in the first toss, then the second toss can be either a head or a tail. In that case, the sample space S will be the collection of all the sample points. So the first branch, you get HH. From the second branch, HT. From the third branch, TH. And the last branch, TT. So in that case, the total number of sample points sums up to be 4, or that is N of S is equal to 2 squared. So if a coin is tossed thrice, then the tree structure would be as follows. If the coin is tossed for the first time, the outcome can be either a head or a tail. If it is a head, then the second toss can be either a head or a tail. If the second toss is a head, then the third toss can be either a head or a tail. But if the second toss is a tail, then the third toss can be either a head or a tail. Likewise, if the first toss you get a tail, then the second toss can be either a tail or a head. If the second toss is tail, then the third toss can be either a head or a tail. But if the second toss was a head, then the third toss can be either a head or a tail. Therefore, the total number of sample points is denoted as the sample space S, which would be equal to H, H, H and H, H, T from the first branch. From the second branch, we get H, T, H and H, T, T. Likewise, from the third branch, T, T, H and T, T, T. And from the last branch we get THH and THT. Therefore, the total number of sample points in the sample space will be denoted as N of S, which is equal to 8, that is 2 cubed. Hence, if a coin is tossed 3 times, then N of S is equal to 2 cubed. So, if a coin is tossed 4 times, then N of S will be 2 power 4. Likewise, if a coin is tossed 10 times, then N of S will be equal to 2 power 10. Now, in that case, it is impossible to draw the tree structure. And that's where we use binomial distribution. Before understanding what is binomial distribution, let us understand the concept of Bernoulli's trials. The prerequisites of a Bernoulli's trials are: first one, the number of trials have to be finite. Second, there are only 2 possible outcomes. That's called dichotomous alternatives. Third, they are independent of each other. And the last one, the probability of success should remain the same for all the trials. Now let's understand the meaning of the first condition. Number of trials are finite. For example, throwing of a coin once, or throwing a coin twice, or throwing a coin thrice. So you can count the trials. Second condition, only 2 possible outcomes. When you throw a coin, you either get a head or a tail. When you solve a true or false question, you either have a true or a false statement. So that's called as dichotomous alternatives. Third condition, that trials have to be independent of each other. You throw a coin once, getting a head. The probability is half. Throw a coin again. Again, the probability remains half. So probability of getting a head in the second trial is independent of getting a head in the first trial. And the last condition, the probability of success remains the same, whatever be the number of trials. So probability of getting a head in the first trial was half. Probability of getting a head in the second trial also was half, as per the previous example. So that's the meaning of probability of success should remain the same. And that happens if the trials are independent of each other. However, let us understand the meaning of Bernoulli's trials using examples. Now let's take up an example where all the conditions of Bernoulli's trials are being satisfied. The question is, a urn has 3 red and 5 white balls. What is the probability of drawing 2 red balls with replacement? So first, total number of red balls is 3. Total number of white balls is 5. So the number of balls in the urn is 8. Probability of drawing a red ball in the first draw, that is equal to 3 by 8. Because probability formula is P of A equals N of A upon N of S. So N of A is number of red balls being drawn, that is 3. From 3 you're selecting 1. And N of S is from total 8 you're selecting 1, that is 8. So probability is 3 by 8. Now the ball is being replaced. Therefore, drawing a red ball in the second draw is also going to be 3 by 8. So the probability remains the. Now in this particular example, we notice that the first condition of Bernoulli's trial is satisfied because the number of balls that are being drawn is only 2. So the number of trials being conducted is countable or it is finite. Next, there are only two possible outcomes, that is either drawing a red ball or drawing a white ball. So the second condition is also satisfied, proving that this example has a dichotomous alternative. Now the third one, the trials have to be independent of each other. Drawing a red ball the second time is independent of drawing a red ball uh, in the first draw. Because the ball was replaced, they are independent of each other. So we notice here the probability of drawing a red ball in the first draw is 3 by 8. Also, the probability of drawing a red ball in the second draw is also 3 by 8. So hence the probability of success remains the same in both the trials. Here the probability of success is nothing but the probability of drawing a red ball in both the draws. Therefore, the probability of success remains the same in each and every trial. It could be either probability of success or even probability of failure. So here the probability of failure would be probability of not drawing the red ball, which should have otherwise been 5 by 8. So the last condition of Bernoulli's trial is also satisfied here, and therefore this is a very good example of Bernoulli's trial being satisfied when the ball is replaced. Now let's just take up the same example, but with the conditions slightly different. The urn contains 3 red balls and 5 white balls. What is the probability of drawing 2 red balls without replacement? So there's a slight change in the question here. So if you notice, the first two conditions of Bernoulli's trials are satisfied. That is, the number of trials are finite. There are only 2 draws, so it's countable. Also, there are only 2 outcomes. That is, either you draw a red ball or a white. But however, the third condition is not satisfied. Now, the third condition of Bernoulli's trial states that the trials have to be independent of each other. However, the second trial is dependent on the first trial, as one of the red balls is outside the urn. So therefore, the removal of the second red ball is now dependent on the first draw. So the probability of drawing a red ball in the first draw was 3 by 8, but the probability of drawing a second red ball is now 2 by 7, as the number of red balls have reduced by 2 and the total number of balls in the urn have reduced by 1. So again, the fourth condition of Bernoulli's trial is not satisfied because the probability of success is not the same in both the trials. So, from this is a suitable example where Bernoulli's trials are not satisfied. Hi guys, hope you all have understood my lecture and I've tried to be as explicit as possible. I guess I've managed to reach across all of you. Thank you so much for watching and hope to see you in my next session of binomial.